All right, welcome everybody to week 2 of distance learning. This week is going to be all about learning about sequences. This video focuses on arithmetic sequences, but before we get into that, what is a sequence? Well, it's basically just a list of numbers where those numbers have some sort of relationship, or there's some kind of pattern between the numbers. All right, so you could think of, this would be a sequence here. Okay. Or you could have something like this. All right. Or even something like this. Okay. Sequences are a huge branch of mathematics. If you look on Wikipedia or just Google it, like list of sequences, there's all different sorts of sequences. All right. But we're going to focus on arithmetic sequences. Before I get into that, though, one way that sequences are studied, basically each number on the list is given a number to refer to it. Okay, so let me just kind of pull one of these aside here. Let me just let's focus on this last one. So this would be like term number 1. This would be term number 2. This is term number 3. Okay, etc. So when we study sequences, we always start counting at 1. All right, so this is the first term, second or third term, right? Same thing here: first, second, third, fourth, first, second, third, fourth, etc. All right. So we're going to focus on arithmetic sequences. By the way, you don't say that arithmetic. Arithmetic is a noun. Arithmetic is an adjective. We're describing the type of sequence. So what is an arithmetic sequence? So that is a specific kind of list of numbers that are related, and there is actually one on this list. I'll go ahead and write that out. So this is arithmetic, and you'll notice the pattern between these is a pattern of addition, right? We're adding the same amount each time. So that makes it arithmetic. So when you think arithmetic here, you've learned the same kind of pattern before. You can sort of think that this is similar to a linear pattern. All right. All right. So, when we're talking about sequences, we don't call it a linear sequence. We call it an arithmetic sequence. All right. Okay. So that is that. Now, what we're going to learn how to do is actually write down equations or rules to represent these sequences, kind of like you did with linear patterns too, right? Y equals mx plus b. It's going to look a little bit different here because what the formula has to do, and I'll just give you some examples. If you put into these are going to act like functions. Okay, you put something in, you get something out. You put in, and I'll just do some number here. That's the term number that you put into the function, okay? And what you get out here is going to be the term value. Okay, so we have the term number and the term value. So you'll notice this is true for this pattern. 1, 2, 3, 4. The fourth term is 10. Right? If I were to put in, I don't know, f of 6, let's say, you should get out 16, right? I don't have it written down here, but 1, 2, 3, 4, 5, 6. The next one would be 16, right? Okay, so that's how the rule has to work. So how do you write this? It's going to look a little bit different than y equals mx plus b, even though this is very similar to a linear pattern. So here's what it looks like. There's actually 2 different types of rules we're going to write too. So we're going to write what's called an explicit rule. Okay, and then we're also going to be writing a recursive rule. All right, now the explicit rule is going to be similar to y equals mx plus b. It's going to look a little different, but very similar. Recursive is going to be a whole other thing. Okay, we'll do that after we do the explicit. So the explicit rule, well, if you think about what needs to happen here, we'll just call the input variable n. Usually, traditionally what's used for sequences is n, not x, okay? So we put in, any number in here, okay? And if you think with linear stuff, we had y equals mx plus b, right? And thinking about, our input variable x is the term number, and the output would be, y here. So let's just see if this works. If I make a linear equation for this, so my rate of change here would be 3, or my slope, and my starting value would be 1. So let's see if this works. If I put in 4 here, does this work? Ooh, it doesn't. It gave me 13. Yeah, that's on the sequence, but it's not the 4th value. Okay. So somehow we need to fix that. This kind of has to do with linear patterns start counting at 0. Okay, that's where your y-intercept is, right? Where your x value is 0, that's where your y-intercept is. Sequences start counting at 1, like this is the first term, okay? In just when we're studying, normal linear relationships, the first value, the first output is at an x equals 0. There was no input of 0 on these. It only goes from, you have to be able to say the number like first, second, third. There's no zeroth. Zeroth is not a word, all right? So yeah, you got to start at 1. So this is going to look very similar to this, except we got to correct it so that basically 1 gets subtracted off this. Because if you think about it, if this was 1 less, this was 3. 3 times 3 would be 9 plus 1 would be 10, which is what we need to get. So that is why the explicit rule, the formula, looks like this. Now the order's also switched a little bit here. A is the first term, or again, thinking back to like linear stuff, that's kind of like the y-intercept, all right? And then this is the rate of change, but we don't call it rate of change here or slope. We call it the common difference, right? Because all the terms in this sequence have a difference of 3. 4 minus 1 is 3. 7 minus 4 is 3. 10 minus 7 is 3, right? Okay, and then here's this n minus 1. We can't just do n. We have to do n minus 1. We have to subtract 1 off of it. So let's actually write the explicit rule for this sequence. Let me go ahead and rewrite the sequence here. One thing I didn't say in the beginning here, and I should have, is, I'm doing these handwritten notes now because I'm not going to assume everybody has a printer to print out the classroom notes I would have given, if we were in the building. So please take notes along with this. It's going to help. If you don't write down every single thing I write down, that's okay. Just make sure you get down what the key points here, right? Okay, so we have to figure out, in order to make a rule for this specific sequence, I'm just going to write down the formula. This is just the generic rule. But for this specific sequence, well, A is the first term, so I put in 1. And then the common difference, well, yeah, it's going up by 3. Usually that's pretty easy to see, but if not, you can always go 4 minus 1 is 3, right? And then you just leave n as n, just like you would leave x as x in y equals mx plus b. And there we go. So there's the explicit rule for this sequence, okay? All right. Let's talk about recursive rules. All right, so these are a little bit different. This is another way that sequences are defined. And I'll just say that for now, okay? And I'll talk more about like why we do recursive rules a little bit later. All right, so what the generic formula looks like for a recursive rule, it's actually 2 separate equations. And let me talk about what this means. It looks kind of intimidating at first here. But what this, how this works here, the recursive rule is 2 parts. Oh, and I actually need to say n is greater than or equal to 2 here. And I'll talk about that later. All right, so the first, basically, this just tells us what the first term is. So part of the recursive rule, this first equation is just like, hey, the first term, right? Because if you put in 1, that's talking about the first term. The first term value is whatever, okay? So that's the same A as over here. If you want to get any other term, you use this, okay? And what this represents here, notice it's in function notation. F is not a variable here. This is a function, this is meaning you actually you put in one less than whatever you're putting in here, okay, and you get that out. So let's actually use this for, again, that same sequence. Before I'll explain that a little bit further, but I just want you to see how this works and prove to you that it works. Okay, so let me write the recursive rule. So this says, okay, the first term goes there, so f of 1 is 1. Okay, and then f of n, all you do, the only thing you plug in here is the common difference, which the common difference we said was 3. Okay, so I've already written the recursive rule here, but let's see, how does this work? Why is this thing here? What does this do? So let me, let's say I want to find, I don't know, f of 4, just like I did earlier. Okay, well, I wouldn't use this first equation because this is only for f of 1. This is for any other term. Oh, I need to say this also. I'll talk about that still. Haven't forgotten about that. And so then you put in 4 here like so. And let me simplify this a little bit. 4 minus 1 is 3. Okay. Now, what this says is you have to find what the third term is. Okay. Now, if we didn't already know what it was, we would have to then go off to the side and figure out what that is. And then that would have an f of 2 in it, and then you'd have to go back and find what f of 2 is, etc., etc. We're not going to do that because that would take a while. But I know f of 3 is 1, 2, 3, 7. Okay, and I end up getting 10, like I should. All right. Okay, yeah, the n is greater than or equal to 2 thing. Why do you have to write that? Well, it's just saying that you can only use this equation if n is 2 or greater. If it's 1, then you use this one. Okay, this does not work for if you put in 1 here, because then you had 1 minus 1, which is f of 0. And like I said, there was no 0 inputs in sequences. It starts at 1. All right, so that's what that's all about. So that might seem like a really funky way to define a sequence. However, some sequences, believe it or not, are more easily defined this way. Not arithmetic ones, I'll just be honest. Okay, part of this unit, sequences, is just to it's a little intro into how sequences are studied. That's a huge branch of mathematics. So the avenue that we do that through is through arithmetic, and then we're also going to talk about geometric sequences later this week. But there are other sequences out there. It's a huge branch of mathematics, like I know I've said enough already, but there are some sequences that actually recursive rules work better for. In fact, this one here, which I said earlier, this works pretty well with a recursive rule. By the way, yeah, I would be. I wish I could say I could give you extra credit. It doesn't. There's not really like a place I can really put extra credit right now for you. In in our current situation, but I would be super impressed if you like wrote a recursive rule for this. Okay, this is a very famous sequence. It's called the Fibonacci sequence. It actually appears in nature a lot, okay? But I don't want this video to go too long. It's already getting a little long, so I'm going to stop there. All right, so that is how you do arithmetic sequences in a nutshell now. All right, so let's do some examples from my.hrw.com. All right, so this first one, all you're doing is identifying if these are arithmetic or not. So you just want to see, do the values go up by a common difference? They have a common difference. Well, let's see, this looks like on part B here, up by 4, up by 4, up by 4, up by 4. Yep, okay, so yes. All right, so that's all that is there. All right, I'll let you guys do the rest of those. Let's do one where you actually have to write the rules. So question 2, here's the table. We have to write the rules here. So we have to identify what A and D are. A is the first term. Well, it looks like it's 17, so first term value. Common difference, well, it looks like these are going down by 5, right? 12 minus 17. So you'd write it as negative, so negative 5, all right? And then we can start filling this in if we want to. It says the sequence is arithmetic because consecutive terms have a common difference of negative 5. Since the initial term 17 corresponds to n equals 1, the explicit rule is, okay, So we'll go ahead and just write the explicit rule here. So again, these formulas are going to be handy to have written down if you didn't write them down before. So it's, f of the explicit is f of n equals a plus d times n minus 1. And then for the recursive, I'll put that over here. That's going to be f of 1 equals a, and then f of n equals f of n minus 1, which, so this represents, I didn't really say this earlier, but this represents the previous term value. Okay, that's the previous term, the whole thing, this whole thing together, okay? It represents the previous term value. And then we have plus d. All right, so let's write the explicit rule here. So we just need to plug in, basically all we're plugging in is our a and d's. We don't mess with the n, right? We want to have a relationship here between the input and output. So we got to leave our input variable and then our output variable, f of n. All right, so f of n equals a is 17 and d is negative 5. And you could write it this way. This is actually acceptable. Or you could also write it like this. Either way should work. I'll make sure that both of those do work on my.hrw.com after I do this part of the video. All right, so the recursive rule would be f of 1 equals the first term, which is 17. All right, and then f of n equals f of n minus 1 plus the common difference. So that should work. You could also write it like, since we have plus a negative, you could write it like this. All right, either one of those should work. This is actually acceptable in the sequence world. You can write plus a negative, all right, just to really highlight what that common difference is. Okay, now you notice there's some other things that it asks for here, which we can get into that. So the explicit rule, which I'll try to squeeze these in here so that I can write them in. So 17 minus 5 times n minus 1. Now, yeah, this is a little bit picky. I wish I could change these problems, but I really can't. Since we're just seeing the table here, we can't assume the pattern continues forever. So we're just saying that n is between 1 and 6, right? Those are the possible n values, all right? So you do have to put that in there. You're just basically saying what the domain is, all right? And then for the recursive rule, well, f of 1 equals 17, right? We said that down here. And then f of n equals f of n minus 1 plus, and all you have to do is put in the negative 5. They already got the f of n minus 1 in there for you. All right, and then what we would put here is we would actually put 2. The reason being is f of 1 is defined here, right? And so n, this can only be used for n is greater than 2, greater than or equal to 2, just like we did in the earlier examples I did on the other notes I did. So just be careful there that this is going to be 1 greater than that one. All right. And I went ahead and checked on my.hrw.com if it would accept this, and it actually doesn't, which really bums me out. So you do need to simplify. If you have a plus and negative, simplify it to a minus. All right. Same thing here, plus and negative. My.hrw.com does not accept that. You need to put just minus. All right. Let me do one more here. I'll do one of these graphing ones. So here we're given a sequence. We just have to list out the terms and then graph the points. All right. And so let me go ahead and do that. And I might switch over to the computer and do this on the computer just so you can kind of see how that works. All right. So the sequence, well, we started at negative 1.5, so that'll be a first term. This is a recursive rule. And then I can see that, it's going down by negative 0.5 every time. So this would be negative 2, and then negative 2.5, okay, etc. So now that I have these, Let me go ahead. I'll switch over to the computer. So I went ahead and filled those out already. So how do you plot the points? Well, what you do if you want to plot the first point here, you just click f of 1, and then you put that on the graph. So it's at, of course, the x value is 1, and then the y value would be negative 1.5. So about right there. Okay, and you just keep doing that. So f of 2 outputs negative 2. So we're at x value of 2, and then y value negative 2. Okay, if you mess up or something like that, whoops, what you can do, it's a little funky how this works. You have to like hit the eraser first, and then I think click this, and then it sort of highlights it, and then you hit erase. Okay, so actually, yeah, I don't know why it does it that way. It seems a little weird. All right, so then f of 3, of course, would be negative 3. So I think I have to go back to here, and let's see if I can plot it again. So negative 2.5. There we go. All right. So yeah, if you want to delete the whole thing, you can hit the trash can there, but just be careful with that. All right. So that's how that works. If you guys have any questions, please feel free to email. I just did a couple examples here. There are a couple others that are a little different. So if you have any questions on those, please email me. I can make another video that would be posted by at least Friday. Email those. The sooner the better. Okay, if you have any questions. All right.